Hello and welcome to NASA Goddard Space Flight Center. Today we're going to talk about one of the most compelling issues of our day, sea level rise. And with me is Dr. Tom Wagner, the program scientist for the cryosphere at NASA headquarters.
And today we're going to take you right behind the front lines of sea level rise research, out into the field with the researchers, and here's what we're going to be talking about for the next hour. So the big thing is this: around the world, sea level is rising. It's going up by 3 millimeters a year. In the last 20 years, it's gone up by 3 inches. And we're trying to understand kind of why that is, but more importantly, we're trying to project out, where it's going to be in the next 100 years. Like it or not, already the east coast of the US is seeing flooding from sea level rise. It's things like the big storms that hit New York and New Jersey, Katrina, but even places like Kennedy Space Center, we're seeing tremendous amounts of erosion. They've gone as far as to make a map of areas that they're going to lose. The city of Miami is getting routine flooding. Now, you might say, well, 3 inches in 20 years, what's the big deal? We can probably deal with what we've already seen, right? But the thing that we're worried about is that as you project out 100 years, it could be more like 3 feet, 4 feet, 5 feet. And the way that society responds to that, the costs rise exponentially.
And one of the things we're going to talk a lot about today is ice. And talk to us about why ice is so important in the topic of sea level rise.
Yeah, so in general, the rise that we're seeing today comes from 2 places. One, as the ocean warms up, it expands, just like hot air in a balloon. But also, too, the big ice sheets, the glaciers of Greenland and the glaciers of Canada and Alaska, the big ice sheets of Greenland and Antarctica, they are waking up and spitting ice into the ocean, and that's the other half of sea level rise.
And so we're going to be bringing in Josh Willis from the Jet Propulsion Laboratory. And then we also have Veena Chu, who is at the University of California, Berkeley, and I believe that's Larry Smith from the University of California, Los Angeles.
Well, sea level has been rising pretty steadily in the last 23 years around the globe. And we've been measuring this with satellite altimeters with our colleagues in the French Space Agency, CNES, ever since 1992. And the net rate of sea level rise is about 3 millimeters per year, which works out to about 1 inch a decade. And it's interesting because the rise isn't equal everywhere. In fact, in places like the west coast of the United States, sea level has actually been falling very slightly. And this is because of the natural cycles in the ocean and the way the oceans and winds can push heat around and redistribute it across the planet. So sea level rise is actually not all that level.
Yeah, but Josh, but overwhelmingly, right? The total amount of sea level rise that we've seen, say, in the 20th century versus the last 20 years, what's it like?
Sea levels have increased, the rate of rise has increased incredibly in the last 100 years or so. In the early 1900s, we were looking at about 1 millimeter per year. In the 1950s, it was more like 2 millimeters per year, and now it's 3 millimeters per year. And in fact, if you look back even farther, the last 2,000 years have had almost no sea level rise whatsoever. So we've pushed the Earth into a brand new regime, and sea level rise is now the norm.
Can you tell us a little bit, though, and I know Michelle was asking about this before we started, how do we actually get to those numbers? Like you're talking about, how do we know what sea level rise was in the 1800s or the 1700s? I mean, today, you pointed out we have these radar altimeters that measure the height of the ocean, but what are the other ways we know?
Well, we've had tide gauge records for 150 years, in a few places even longer. But in the last 2,000 years, we've actually been keeping a record of sea level rise in the sediments in places like North Carolina. There's a salt marsh there, and it turns out that the land there is steadily sinking, just very slightly. And as the water creeps up the land, it leaves behind a record in the form of tiny little bugs and critters that die and live in the sediment. So people drilling sediment cores have actually been able to reconstruct a very accurate sea level record for the last 2,000 years. And what it shows is not much until the last 150. And that's when sea level rise really took off and we began to see the rates we have today.
Now, one of the things I think people aren't aware of is just how many resources NASA has to study what's changing on the Earth. I think that right now there are actually about 19 different spacecraft that are orbiting the Earth, taking readings from everything about the oceans, the land, and the atmosphere. What are some of the missions that you specifically work with, and what are some of the data that you take?
Well, the best mission of all those is the JASON missions, in my humble opinion, because those are the ones that I work on. But I think, as you say, there's a whole bunch of missions. The JASON missions measure sea level directly from space. Missions like GRACE actually weigh the continents and the oceans.
Yeah, that's really excellent stuff. You know, and the GRACE mission that you mentioned is one of the things that I find really compelling, that in fact there's so much water melting off these glaciers, it's actually changing the gravity field of the Earth. I mean, could you tell us a little bit about how GRACE works and how that measurement is made?
Yeah, GRACE is really fun. In fact, it's made of two satellites. They're named Tom and Jerry, and they chase each other around. And whenever the first one goes over something heavy, the pull of gravity causes it to speed up just slightly. And the two satellites actually measure the distance between each other, and you can use that information to infer the mass of the thing you're flying over.
Hey Josh, I got a question yesterday from a reporter. Can you just talk a little bit about, okay, look, the radar altimetry, the record we get, and how we see things like tide gauge, how do they work, and how does that all come together?
Yeah, well, so the satellites that measure sea level are really amazing. They're 800 miles up, and they can measure the level of the ocean in about a 6-mile footprint with an accuracy of just 1 inch or better. So it's an incredibly accurate piece of equipment. It measures the entire planet once every 10 days, and by averaging all of that data together, we can actually get an estimate of the total level of the ocean, the total volume of the ocean, with an accuracy of about 1/2 a centimeter. So it's really tiny. And they're really incredibly accurate, these missions. In fact, we've often compared them with tide gauges. So in a few key locations, we have tide gauges that have been running for the entire 23-year-long record, and they've allowed us to help tie together one satellite after another. We've also been lucky enough to have each satellite survive until the next one was launched, so beginning with Topex Poseidon in 1992, and then continuing with JASON 1 in 2001 and JASON 2 in 2008, and we're hopeful to launch JASON 3 sometime in the next 6 months, something like that. And so we're really excited about our, about our record of sea level rise, because it's one of the most accurate means we have for charting how humans are changing the overall climate on the planet.
Hey,
because
Josh,
if you think about it, the Earth is 2/3 ocean.
Great. Hey, thank you very much. And I know we're going to have you back later in the show. But coming up next, Michelle, I think we have a video.
Well, yes. In fact, we're going to be speaking to a scientist that actually does research sponsored by the NSF in Greenland. So if we could roll the video about Mike Beavis and his work, please.
Yeah, this is the champion glacier of Greenland. This is Jakobshavn. So this is the one that's losing the most mass. It's losing so much mass you can see it in space. They can see gravity change. The loss of the mass is causing gravity to change. Yeah, we've got instruments all over the place, but this is going to be one of our most important ones. There's the antenna, and it's bolted to the rock. So this ice is the weight holding the elastic Earth down. As that weight is released by the loss of ice, the ground is rising. That antenna is rising.
And you can measure that? We
can measure that. That's recording data 24 hours a day, year after year after year.
Hey, so one of the other things too is how do we take this kind of measurement you've made here with literally a GPS device out in the field banged into the rock? How do you combine that with satellite information to get a big picture?
All the techniques have got their strengths and their weaknesses. So there's, for example, GRACE is incredibly precise. It can measure a tiny change in mass, but it's not always sure what that mass is. It could be the mass of the rock is changing if you've got post-glacial rebound, or it could be the ice, or some combination. So in that case, you have to make a correction for what the vertical movement of the ground is, so you're not spoofed by a rock change rather than an ice change. It turns out that correction is about the same size as the answer. So if you get the correction wrong, you start to get errors in your answer. So GPS can help with that because it's going to sense both the elastic rebound and the slower viscous rebound. And in general, you want to combine different instruments so that each instrument's compensating with its strengths for the weaknesses of the other instruments.
And this is something that I think most people don't think about, the fact that the Earth, solid land itself, is actually elastic, that as the ice melts, it's rebounding.
Yeah, like for example, I first realized this in a big way when we were looking at GPS stations in the central Amazon basin. And we noticed that these stations are going up and down like 60 millimeters every year. And then we looked at the height of the Amazon River, and we saw that as the river was going up, the ground was going down. And as the river went down, the ground was going up. It was just the weight of the water deflecting the surface downwards.
You've got, how many stations do you have in around Greenland?
We have 50 in Greenland, and we have sort of similar number in West Antarctica.
Wow. And any fascinating results from any of those stations in particular?
I mean, for example, you see the places where people already knew was the major ice loss, like Jakobshavn Glacier or Thwaites Glacier, is where you also see the ground rising the fastest. One of the interesting things is we see that almost everywhere it's accelerating. So in Jakobshavn, it was rising about 12 millimeters a year in 2008. By the end of 2012, it was going up like 32, 33 millimeters a year.
The ground is coming up 33 millimeters a year.
Yeah, more than an inch a year, just because of the release of the weight of the ice.
Wow.
God. Hey, now is it hard? It must be pretty tough to put these stations in the polar regions.
It's challenging because they've got to run all year, right? And so for a large part of the year, the winter, there's no sun. And so you have to charge up huge banks of batteries so you can get through the night. So these are very large, heavy systems. I think we spent like $2 million on helicopter fees just to install GNet. All this weight goes in, and then the sun charges those batteries all summer long, and then you can run all through the winter and send the data out via satellites.
God, amazing.
Now, the Earth rebounding, actually sort of bounding up after the weight is taken off, it must go very slowly. This isn't something that just happens immediately. Is there also something about the history of the ice and how the ice has changed that's in your data as well? Yeah,
there's actually two ways the Earth behaves. There's an elastic response, which is literally instantaneous. So as you lose the ice, there's an instantaneous adjustment. But then the Earth also behaves viscously. It will flow away from a stress, like a weight. And that in most of the world, that takes 10,000 years, say, to happen. So the ground all around Fennoscandia is rising now, not because of what's happening now, but because of what happened, 12,000 years ago when the ice suddenly disappeared.
God, amazing. Hey, Mike, thank you very, very much for joining us. We really appreciate you coming in.
Now we're going to take a really close look at what's going on inside the ice. And we're going to start with looking at the very surface of the ice, because that's where a lot of the melt is happening.
A short helicopter flight from the edge of the Greenland Ice Sheet lies a 27 square mile network of streams draining the surface of the ice as it melts in the sun. This summer, an interdisciplinary team of NASA-funded researchers set up camp near the end of that network, where a large melt pond emptied into an outlet stream, which then a few hundred meters later disappeared under a snow bridge and into a stunning and dangerous moulin, a hole in the ice leading far below. The team had many tools at their disposal, including drones to map the area and provide a comparison for satellite measurements. They also employed what was essentially a boogie board mounted with a Doppler instrument measuring the depth of the river and the speed of its flow. Working in shifts, they conducted 72 straight hours of measurements across the stream. They also made a series of short helicopter flights upstream and placed floating sensors into 3 tributaries to measure the water as it moved. About an hour later, the team was thrilled to see all 3 drifters pass by their camp within a matter of minutes, presumably relaying a few last observations before disappearing into the Moulin. But measuring meltwater runoff was only part of the effort. Other researchers joined the team to measure the albedo, or the brightness of the snow and ice in the region. This albedo determines how much of the sun's energy will be absorbed, and therefore how fast the surface will melt. From helicopters, researchers measured incoming solar radiation and compared it to the light reflected by the ice. They also imaged the ice using a digital camera, creating these beautiful high-resolution mosaics to better map the region. After a short but intense field season, the researchers packed up camp and left the ice, hopeful that the data they'd acquired could help shed light on the future of the Greenland Ice Sheet.
Now, we're going to go to some of our colleagues who are actually out at the Jet Propulsion Laboratory today, and we're going to talk to Larry Smith from the University of California, Los Angeles, and Veena Chu from the University of California, Berkeley. And Tom, maybe you can ask them about the research.
Hey, Larry and Veena, thanks for joining us today. I don't know if you could see it, but we just showed some video of you guys out in the field. Can you tell us a little bit about your field network and what it is that you're measuring?
Sure, absolutely. Our project focuses on the hydrology of the surface, of the melting surface of the Greenland Ice Sheet. And this is a surprisingly little studied field in glaciology for this part of the world. But it's an important one for society and for sea level rise because already melting of the surface of the Greenland ice sheet is thought to contribute about half to 2/3 of the total mass loss from Greenland as measured by GRACE, for example, with the remainder being from solid ice calving losses. But these predictions are very often based on regional climate models. And so what our measurements are attempting to do is to provide some of the first real-world in situ measurements of meltwater production and runoff on the surface of the ice sheets to try to verify and validate these model predictions of future sea level rise.
Hey, now Veena, you're one of the people that goes out in the field and does all the hard work, right?
Yeah, I've been going there for about 8 years now, yeah.
Hey, so tell us about some of the gear you take into the field and what kind of measurements you actually make.
Well, the first goal is just to get the camp set up. So we have multiple tents and all our camping gear, but we also have, we're measuring discharge, so the actual amount of water going through these rivers. So we have a sort of like boogie board setup that we take across the river. It's a sort of Doppler system that measures how fast the water is flowing and how deep the water is flowing.
Yeah, so what I can get over though, it seems like you guys are also talking about, it seems like there's been a big increase recently in the amount of melting that's gone on the surface of Greenland. And tell us about that. Tell us kind of what you're seeing. I know some of the rivers flow pretty fast.
Sure. The satellite record shows that, while bumpy with warmer years and cooler years, in general, the overall trend has been an increasing extent, intensity, and duration of the melt season on the surface of the ice. But these coarse resolution satellites, often microwave-based, don't have the granularity to see the fine-scale structures and physical processes that are routing this water off the ice sheet. And this is actually very important because one of the key questions is how much of that melt on the surface of the ice, particularly as it expands deeper into the interior, how much of that meltwater is actually escaping the ice sheet to contribute to sea level rise? At the moment, our assumption is that all of it does, but in fact it's entirely plausible that perhaps some of it, some fraction of it, is retained by the ice sheet, refrozen at the surface or stored within the ice sheet. And that's why these field measurements and also higher resolution satellite and airborne technologies such as Operation Ice Bridge, such as the Worldview series of satellites, these provide an additional finer scale resolution to study these processes and confirm that indeed this melt on the surface is escaping the ice sheet to the global ocean.
Thanks. Hey, Michelle, I understand we might have some video.
That's right. We actually have some video about what it's like to work in these pretty extreme conditions.
This is the best time. How lucky are we to come up here in Greenland?
Something about this place gets under our skins, and we keep coming back. You can only reach this area here with helicopter.
We're camping in the ablation zone. It's very wet, as you can see.
Water is running everywhere. It's flowing into these chutes and channels, which are getting bigger and faster with every second. If someone, goodness help us, were to ever fall into one of these, there would be no hope.
So we are very careful with our safety procedures. The most important here is that we all come back home.
It is a difficult environment to work in. It's cold here. There are problems with equipment. When you have problems with equipment, it's hard to get replacements. It takes weeks to get things shipped up. The temperatures, and in my case, the sediment load of rivers makes it hard to actually do the sample collection, but it's also the most inspiring and thrilling environment to work in. Every day I go out in the fields, I look around at my environment, the ice, the river, how dynamic it is, and it reminds me why I'm out here, and I absolutely love it.
Yeah, one of the hardest things there is just working in those environments. I mean, the fact is that we're working in an area that not many people work. Up till the last 6 years or so, people don't really work on the ice sheet when it's melting all around you. Just even camping is hard. And we're dealing with limited helicopter hours. So if you need more equipment or if something breaks, and one of the big things that we dealt with was how do we keep batteries warm, and how do we set up camp so that rivers aren't flowing around us and melting out around our tent.
Oh, wow. Hey, can you tell us a little bit about what happens? Where does the water go? We understand a lot of it doesn't say flow directly off the ice sheet, but it goes into these big holes in the ice?
In fact, these sinkholes, they're called moulins. In fact, what we've seen is that all the rivers on the ice, the majority of them actually go into these sinkholes rather than forming long rivers to the end of the ice. So we particularly set up these camps right near these moulins so we can measure how fast and how much water is going into them. And like you were saying before, the significance of these moulins and these sinkholes is that it takes water into the bottom of the ice sheet. And that's where it can really affect how fast the ice is flowing. And the more that's melting, the more water can go inside. What we've seen in some of our high-resolution satellite maps is that there are thousands of these holes, thousands of these rivers draining into the ice sheet, and at higher elevations than we have ever really known about before. Just with the availability of better satellite imagery, higher resolution data, we're able to actually see just how many of these rivers are bringing water into the bottom of the ice sheet where it can affect the ice dynamics and the ice flow.
Joining us now is Dr. Sophie Nowicki. We're going to talk a little bit about the actual work that we do to understand what's going on inside the ice sheets. And first, we're going to show you some more video from NASA's Operation Ice Bridge. Hey, so Sophie, tell us what we're looking at right now.
It's a very nice image. Basically, you're seeing what is white is ice flowing into the sea. Those little parts that are kind of darker. And you can see that the ice has very complex features. A different type of river of ice, of river of water. You saw those very different to what Larry was showing you before. This is really hard ice.
This is actual ice. This isn't water going in the ocean. This is something that's like an ice cube out of my fridge.
Yes, and then you can saw this little ice cube. And so what you can map now with this, with our measurements tools, capabilities, is the actual height of the ice. And as time goes, you see this is the height of the upper surface of the.
Okay, so over here we've got our vertical axis. That's meters. That's height of the ice. And then what, this is along the flight line itself?
Exactly.
Okay, and this is the height of the ice going down, and that's the water out there.
Yes, and so you can see the big drop, that's where the ice meets the ocean. And this drop just like is going backwards at the moment in time.
Whoa, so that's the ice front backtracking.
All the way back.
You had like a 5 kilometers jump in time. So it's a very, even though you think about ice as an ice cube, it's actually very dynamic. It kind of moves back and forth.
So
now let's talk a little bit about how this data was taken, because this is very dramatic, right? Operation Icebridge is an aircraft, and the aircraft actually flies over Greenland and Antarctica, and it bounces lasers off the ice.
It does. One of the measurements that they do is that they bounce lasers off the surface and it goes back, but they also can have other measurements, which hopefully we'll see later, that goes through the ice. And what's amazing is that Greenland is so big. It's about a quarter of the size of the US, but NASA has flown over quite a big portion of that over the last few years.
So the research project that I was involved in this past week is looking at the calving of tidewater glaciers. So there are fjords here in Greenland where the water comes right up to the face of the glacier. The water down below is warm and salty. There's meltwater that comes shooting out through large gaps at the base of the ice sheets right into the water, and that creates these turbulent plumes of water that draw yet more warm water in. And it's this interaction between the ice and the ocean that may help to regulate how quickly sea level will rise. Our climate models, because they're global and have to run for centuries, we can only resolve down to scales of order a few kilometers, and yet all the action at that ice shelf front is happening on scales of just a few hundred meters. It's fun and exciting, and it's stunning to watch. But one of our challenges is figuring out how to incorporate all that action that's happening at small scales and put it into global scale models. It's absolutely essential. It's the processes that are going on in the fjords and up on the ice cap that control how the system is going to evolve. We know that sea level is rising, we know that the ice sheets are losing mass, but we need to understand why, because it's only that why that helps us to project how things will change in the future.
And it turns out that why is actually kind of a complicated question to answer, because we cannot see directly inside the ice sheets.
Yeah, and one of the things that's always impressed me is when you look at the modeling results that came out of like the IPCC report, our best projections for future sea level rise. Sophie, you were involved with that. There's a huge spread. Like we talk about sea level rise in the next 100 years being, is it a foot? Is it 5 feet? Could it be more? Tell us about how those models are made. Like, what goes into them as a start?
So you have to think of a model as a virtual laboratory that I'm building. I'm putting all of the things that I think that matter. So the snowfall, the bedrock, how the bedrock reacts, and then basically we let it mix together and kind of explore and understand the way that if I poke my system, what's going to happen. So if you look at my projection, there is a spread because we try lots of different scenarios. Where we want to kind of see, is the snowfall going to matter more in 100 years? Is it going to be the ocean? And as Dan just showed in the video before, ice-ocean interaction is quite complex.
But take us back to the basics just for a second, right? So you talked about, we've got this numerical model that describes how the ice flows into the ocean. It also takes out how much snow falls on the surface of the ice. But then you mentioned something like the bedrock underneath. How does the bedrock affect an ice sheet model that's used for sea level rise?
So that's a good question, because before Operation Icebridge, we had no idea what the bedrock looked like. And that's one of the good, for me, one of the most beautiful return about Operation Icebridge is the shape of the bed. It matters because it tells me how big my ice is, my volume of the ice that's available to flow. So it's the one thing, how much ice do I have?
How much ice is there?
But also, it also matters because, imagine you're skiing downhill. You go quite fast, because it's going downhill. So the ice is the same thing. I'm going to go go down quite fast. But if I have to slide down, if you have to ski uphill, you have to really do lots of hard work. It's the same thing for the ice. If the bedrock changes and I have to go uphill, it's hard work for me.
Okay.
And this must affect the way that the ice is melting. If there's this terrain underneath Greenland that we're only just aware of. We discovered this giant canyon system from the data from Operation Icebridge.
That is correct. And then also those canyons that are basically the size of the Grand Canyons, this is also where some of the water that Larry showed you going into the surface is going to be trapped and route down, and those are going to affect my ice flow.
So, okay, but one of the other things too with the bedrock, so we've been talking recently about Antarctica, and last year we had those papers come out where we said, oh my gosh, part of Antarctica is unstable now and sea level is going to rise rapidly. Tell us about what they found and how that affects models.
So they basically, as Operation Ice Bridge was flying over, they managed to kind of saw those big bump in the bed. And those bump in the beds means that when the ice is changing due to a warmer ocean, when the ice is retreating back into the interior of the ice sheet, if I have a little bump, then I can basically anchor myself. And that's basically why knowing the bed is so important, because do I have a place to anchor myself as I'm collapsing, or do I don't have a bump in the bed and therefore I keep on going?
So literally, when you retreat past the anchor point, the ice pops up and it can begin almost to float.
It can begin to float, and then it's just like, when you're
and we're talking about hundreds, ice that's how thick? Hundreds of feet.
Yes, it is hundreds of feet. So it's quite impressive, actually, how dynamic the ice can be.
Okay, so getting back to it, right? Because people, I think one of the problems that people get into is they say, okay, scientists, give us a projection. Somebody wants to put a power plant in, they want to know how high sea level is going to rise in 100 years, right? We give them this spread that goes, in 100 years from now, it's anywhere from 1 to 5 feet. How does a result like that affect the projections?
Yeah, it's hard, because when you have those projections of with the right range, it's because it's due to the fact that we're using different models, we're using different data sets. Sometimes, I might be using my bed and then somebody else is using a different bed. And so those all come to play in a way that we couldn't know. And that's why the spread is actually, at the moment, it's good, because we have something to try to work forward to refining, and NASA is doing a huge amount of work to refining this spread, because of course I'm not happy to tell you I don't know if it's going to be 1 feet or 5 feet. I would rather be able to tell you it's going to be 2.5 foot for planning.
Right.
But at the moment, this is just the way it is. The future is very uncertain, and that's what we're dealing with.
Hey guys. Well, yeah, the oceans are definitely eating away at the Greenland ice sheet from the edges. We've known pretty well for a long time that the surface is melting. We can see that melt from space, and Larry and Vina were out on the ice watching the rivers of meltwater dive down into these moulins. But more recently, research has started to suggest that the ice is actually being eaten away at the edges. Remember, a lot of these glaciers, which carry the ice away from the ice sheet and into the oceans, actually sit right in the oceans. They literally have a toe in the water. And that makes them susceptible to warming and the intrusion of warm water from the edges, which can melt away at the glaciers.
Tell us a little bit about the continental shelf around Greenland, its relationship to the ocean, and that's relationship to the ice.
Yeah, well, what's really interesting, Tom, is that the water around Greenland is sort of upside down. You have warm water underneath a layer of cold water. Normally, it's the other way around, right? Warm water rises. But the waters around Greenland are actually what we call inverted, meaning that the warm water is actually at depth, and it's at depth because it's extra salty. This water comes from the Atlantic. It's a very salty ocean. The cold water comes from the Arctic, and it's very fresh, so it sits on top. And what this means is that the warm water has to climb up the continental shelf and reach into the fjords in order to interact with the glaciers. So one of the things we're really interested in is just how that water might get there, what pathways it might take along the continental shelf.
We're showing some video now of what it's like to do that work. Can you tell us about the oceanographic measurements that you actually make and what goes into making them?
Yeah, absolutely. So this is really exciting because this ship has sailed into a fjord, which is a long trench carved by an ancient glacier and is now filled with water. And they're deploying instruments. Some of them are called moorings, which sit on the bottom and collect data for a long time. And some of them are CTDs, which are one-time measurements of the ocean. You can see the ship pushing away icebergs and folks paddling through the slush. It's really hard work, and it's really difficult. And right now we actually have a ship, the Cape Brace, which you see right there at the end of the video, which is collecting data about the shape and depth of these fjords, because that's really important for understanding how that warm water can climb up onto the shelf and reach the glaciers.
So tell me a little bit. You go out and you make a few point measurements, right? How do you synthesize all this stuff together, to get at those big, what are the big picture specific questions you're trying to answer? And how do you put all those things together?
Well, most people would tell you a model, but I'm going to say you just need a whole lot of those point measurements. In fact, we've only just begun to study the oceans around Greenland. While there have been a lot of moorings placed and some surveys that have happened for a long time in a very few places, the vast majority of the area around the island of Greenland is just unmeasured in terms of the ocean, not just how salty or how fresh or warm or cold the water might be, but even how deep it is. In fact, there are huge areas around Greenland where we have no depth measurements, so we don't know if there are deep trenches or sills that this warm water might have to climb over. So we have a whole lot of observations to make, and right now we've actually begun making those kinds of observations with the new mission Oceans Melting Greenland, or OMG.
Yeah, and I think we're going to show some video now of how the aircraft work for OMG.
So describe this mission here.
Yeah, so what you're seeing here is an aircraft measurement of the height of the ice. And this is a measurement that will fly once a year. We're also measuring ocean temperatures using deployable instruments. So these are being dropped out of the back of the aircraft. They fall through the water and measure temperature and salinity. And then a small float actually radios that data back to the airplane. So those two campaigns will happen every year for about 5 years. But we also have ship-based measurements of the seafloor depth. And finally, an airplane that measures gravity. And the gravity measurements are important because that also tells you about the depth of the seafloor. Whenever you fly over a trench, the pull of gravity is a little bit weaker. And that's how we can infer, in a lot of places where we can't drive the ship, we can infer how deep the water is. So all 4 of these campaigns are part of the Oceans Melting Greenland mission, which started this year. We have the ship in the water right now, and next year we'll be starting to fly the airplanes.
A really dramatic interface of the land and the ocean and ice. Can you tell us, is there anything special about the geography of a fjord that affects how the ice and the ocean work together?
The glaciers dug out these trenches on their path off the land and towards the ocean, and left behind avenues for this warm water to sneak up from the deep and interact with the glaciers. So a lot of what scientists are focusing on today is this interface where water meets ice meets land, because that's where the real action is in terms of the ocean-ice interaction. As we heard about before, a lot of the meltwater from the surface actually digs down through the ice sheet, and it finds its way to the ocean actually at the bottom of the ice. So it often, or in some cases, it comes out right at the bottom of the ice, and then because it's light and fresh, it surfaces. That can pull warm water in towards the bottom of the glacier and increase melting, and that's what we're really looking for with OMG.
So here we see these little arrows are indicating the flow of the ice?
Right, so here we are. The blue is the ocean. Those blue lines are showing the direction of flow of the ice. And you can see what happens is kind of slow on the sides. Then it gets into this racetrack in the middle and it goes out to the ocean. And what's so fascinating about this is that you can see kind of right at the front, this stuff is like, some people call it like the cork in the bottle, and that these processes that Josh's team is studying under OMG, they're looking at how the ocean causes the ice to fracture more easily, pull that cork out of the bottle, and let the ice behind it speed up and really dump in the ocean.
We're really seeing just how many complex interactions are going on here, that as the air warms, that affects the ice, as the ocean warms, that affects the ice as well. So this is one of the reasons we see such dramatic changes at the poles.
Yeah, and it's one of the reasons that NASA gets involved in this work. You need a lot of new technology to do this. A lot of it's remote sensing, which means we make measurements from far away, from aircraft or satellites. But then we kind of take the view of trying to model it and pull all those little pieces together. This is Jakobshavn Isbrae Glacier from Greenland, one of the most important outlet glaciers. It drains quite a bit of Greenland. This is where the front of the glacier was in 1850. This is where the glacier was today, and this is actually really recent stuff from just a few days ago that shows you just how much ice can be lost over the course of a couple of days.
So we're actually seeing the ice cracking up right there. That's the change that we're looking for?
Right.
Yeah.
But I mean, and you're talking, again, this is like kilometer scale type events, you know. This ice actually, here's some footage of the thing itself. So there's some great pictures of these where what people have done is compare the sizes of the chunks of ice breaking off to like buildings. And so some of these chunks you're looking at, they're like as big as the US Capitol building.
I think, you know, one of the striking things about that image of the ice breaking off is the timeline that's associated with it. If you look carefully, that data goes back to the late 1800s. So this glacier has been retreating steadily for the last 150 years, and it's happening, you know, on a glacial timescale very rapidly. So we're really interested in trying to study just how these things are proceeding and what the role of the ocean might be in helping to drive them. Clearly, if those things are being eaten away at the edges, we need to be able to quantify that if we ever hope to predict sea level rise into the future.
Hey Josh, now you are kind of a man who's a jack of all trades. We're also going to talk now about Jason 3 as we kind of finalize our program, and we're going to start talking about what are the things that are coming next for NASA. Can you tell us a little about Jason 3? And I understand we have a picture of it to put up that you might talk to.
Well, the Jason missions are really, in my opinion, one of our most important means of measuring the human impact on the global climate, because these missions measure the total volume of the ocean basically once every 10 days. We can really watch how the entire planet is responding to climate change with kind of one single number. And these satellites have been providing that record since the early 1990s. And we're really looking forward to Jason 3 in order to continue that record. You know, a lot of folks ask, well, what's new about Jason 3? And I like to say, well, it's going to measure the next 5 years instead of the last 5 years. And really, that's a big deal in climate science. A lot of what we need are long records to be able to compare what's going on to the ice and the oceans today with how they were decades ago.
I think what people forget is some of the big components of the Earth's system, they behave on decadal timescales, like the Pacific Decadal Oscillation. So tell us a little bit about
absolutely.
that.
One of the things that the satellite altimeters do is they measure sea level not just everywhere around the globe, but in each place around the globe. So you can see clearly where the Pacific Ocean is rising quickly, like in the West Pacific, near Indonesia and Australia. They've been getting hammered with rates of sea level rise that are 3 times as large as the global average. So they're getting way more than their fair share of sea level rise. We, on the West Coast here in California, have been getting less than our fair share. In fact, in some places, sea levels have actually fallen very slightly. And that sometimes can give us a sort of false sense of security. You know, global sea levels are rising, and we're going to have to pay that debt of sea level rise that we didn't get in the last 20 years, probably sometime in the next 20 years.
Josh, thanks a lot for joining us today. We really appreciate it. Good luck with that mission.
Thanks.
So we've talked a lot today about all kinds of different scientists that are studying ice, that are studying ocean level rise. And one of my big questions is, what comes next?
Yeah, so NASA's actually got a bunch of missions coming up that's going to help us with this. You know, so the next thing that's going to happen is the GRACE follow-on mission, which we're hoping is going to provide a higher resolution look at this mass loss and change of the ice sheets. Then after that, we have the ICESat-2 launch. And ICESat is this laser altimeter that goes and literally, it's like a laser pointer in space, tells us very precisely the height of the ice over the entire planet. It even also gets used to measure global forest heights and abundance. And so then after that, we will have what's called the NISAR mission, which is a mission jointly with India. That's a new radar mapper that's going to tell us a lot about how the velocity of the ice flow to the ocean has been changing. So what we're really hoping is that we can pull all this information together and really narrow down those error bars on the estimates of sea level rise and help society plan.
And it may surprise you to know that so many NASA resources are being used to study the ice and study the Earth. So when people ask you the question, why is NASA studying ice? What's your answer?
You know, it's a pretty simple answer. This is a global question. You need to measure all the different parts of the system at once, and you need different technologies to do it, and new technologies. And that's what NASA excels at, you know? And so we build the satellites and the technologies and the aircraft to make these kinds of measurements, and we put people in the field to help pull it together. But I should say, too, we also work with our partners. You know, the National Science Foundation, the Department of Energy, NOAA, the USGS, they're also all working on this problem, and we all work together.
So NASA is studying many different aspects of how the oceans are changing. And this is something that's happening right now. This is something that's going to affect all of our lives, no matter how close we actually live to water. So on behalf of NASA and all the scientists at NASA, one of the things I can say is our Earth is changing. And at NASA, we're on it.